Okay, good morning. Let's start this morning session. It's a great pleasure to have with us Professor Angel Plastino. Professor Angel Plastino is emeritus professor of the University of La Plata, Argentina, which was the first physics department of Argentina. Is that correct?
Yes.
The first physics department of Argentina was at University of La Plata. It's one of the biggest universities of Argentina. Is it the biggest or?
No. Number 3.
Number 3. Okay. He was rector for twice of University of La Plata. And the curious thing is that he is a physicist, he is a researcher. And if you look at his vast list of publications, you cannot tell the period that he was a rector. So it's a great pleasure to have with us Professor Plastino to talk about entropic force and gravitation.
Good morning. It is a great pleasure for me to be here. I like the CBPF very, very much. I am very happy when I am here. And I thank the organizers for giving me the chance to be once again at the CBPF. Well, I am going to discuss a bit a work in collaboration with Mario Roca, who is also from my university. And the title links something which is rather old, the entropic force, which is, as I tell you, is not a novel idea. It has many years already. Polymers, for example, are based, the description of polymers is based on entropic forces. But the new idea is, that is not from us, it's from a professor in Amsterdam called Verlinde. And the idea is to link the idea of Verlinde is to link gravitation with the entropic force. So I would like to divide my discussion into 3 parts. First, tell something about what is an entropic force. Second, I'll try to say something about Verlinde's ideas. Verlinde is the one who originated all this movement towards a new understanding of gravitation. And finally, our statistical mechanics contribution to Verlinde's ideas. What is the motivation? Mainly it's the motivation of Verlinde. The question is dark matter. It's been known for many years, at least from the 1930s, that we need dark matter to account for how celestial bodies move. For example, stars, they move more rapidly than could be understood using Newton's gravitation. So with the mass that is visible. So we need something else, and a Swiss man who discovered this fact in the 30s, in 1934, he coined the word dark matter. Now the question is that in the last 30 years, many people with very sophisticated equipment have failed to detect dark matter particles. That is 30 years with a lot of equipment and a lot of money and no results on dark matter is a lot of time. So this opens the possibility that maybe gravity has to be modified. That in order to account for how stars, for example, orbit in galaxies, you have to change not the matter, but to change gravity. Some very recent astrophysical evidence favors modified gravity theories, and there is a very recent and nice article in Scientific American where you can read about this new astrophysical evidence. I don't remember the name. But it's the number of August of this year. Now, there is something that must be said about why humans need an entropic force. And this is because searching for causal interpretations is hardwired into our brain, while statistic probability interpretations are soft-wired into our brain. This is not mere talk. This discovery, based on thousands of experiments, was done by a team of people under the leadership of Daniel Kahneman, and they were awarded a Nobel Prize for Economics in 2001 for this discovery. So we intuitively look for causes, but it is somewhat hard for our brains to understand probabilistic interpretations. This is bad news for statistical mechanics, but that is how biology works, how evolution works. It works towards searching for causal interpretations because, as we will see immediately, what is called entropic force is just a surrogate causal effect of what? Of the tendency for entropy to grow. So the entropic force is a force that is generated by entropy. This force is very easily verified in the laboratory and is very common in all living matter. Our cells, everything in our bodies and in the body of all animals uses entropic forces. Uses entropic forces via osmosis. Okay, you know what osmosis is. You have a device with two chambers separated by a semi-permeable membrane. This idea of the semi-permeable membrane will be used by Verlinde. One side has water with low solute concentration. The other side has water with high solute concentration. And water can flow through the membrane, but the solute cannot flow through the membrane. A potential is established between both sides of the membrane such that the water will flow in the direction of higher solute concentration. In doing so, the water flow will generate a pressure head, osmotic pressure, and since pressure is force per area, the osmotic pressure is connected to a force that is being applied over an area. That force is the osmotic force, and the osmotic law is right there. Force, osmotic force, times displacement delta x equals temperature times change in entropy. Now we come to why the interesting entropic force has risen now, since Verlinde proposed in 2011 to interpret the force in Newton's second law and gravity as entropic forces. So this seems very big as an statement, very grandiose as an statement, and very strange as an statement. But that is what he said. He published it in JHP in 2011, and it has more than 3,000 downloads since then, and more than 700 sites. Now, I call attention to this nice article by another Dutch. Verlinde is Dutch, and Nico Ross is also that. He shows in this nice paper that he can explain Brownian motion using entropic force. And already in the 80s, Neumann showed that you can also explain random walk using entropic forces. So the ideas of random force are rather old. So it is interesting to understand or to accept that something so ordinary as Brownian motion can be fully understood in terms of entropic forces. Entropic forces are something very common, and there is nothing strange about entropic forces. What is strange is to link gravitation to entropic forces. The entropic forces by themselves are very well known. So that allotropic force is an emergent phenomenon resulting from the tendency of thermodynamic systems to maximize its entropy. Okay, here is a short explanation of random walk based on the idea of a radial force. Which is t times the derivative of the entropy with respect to the radius. This explains somehow a random walk example. So here is a more concrete date. 1977, Journal of Chemical Physics, Newman again proved that a radial force can be written as temperature times derivative of the entropy with respect to the radius at constant temperature. So entropy works as a potential for the entropic force. So this is what distinguishes entropic forces from other forces. Entropic forces are not natural forces. They are emergent forces. They emerge because they have the entropy as a potential. So this is the central idea. The entropy is the potential out of which the entropic force arises. Once you accept this, there is nothing strange with the entropic forces, but they are not natural forces. Okay. The most important phenomenon that can be understood and that essentially needs entropic force to be understood is the phenomenon of polymerization, a folding of polymeters that, okay, I told you already of osmosis. Remember this osmotic law because it's important in what follows. According to Verlinde, all these examples according to him suggest that gravity could be also an entropic force, and he makes some very convoluted explanation that I will go into transcribe for you. Okay, we need the concept of event horizon, but that was discussed on Monday, for example, on Monday afternoon. So I don't need to go over that. The holographic principle is something that Verlinde uses. This is a principle invented by another Dutch. We have a lot of Dutch people here because Verlinde is a Dutchman. And Nico Ross, which I mentioned in connection with Brownian motion, is a Dutchman. And The holographic principle was also invented by a Dutchman. He is a Nobel Prize called Toff. This principle says that the description of a volume of a space can be thought of as encoded on a lower dimensional boundary to the region, like a gravitational event horizon. According to the holographic principle, space is a device to describe the positions and movements of particles as storage space for information associated with matter. Verlinde assumes that information is stored on surfaces according to this principle. We imagine that this information about the location of particles is stored in discrete bits on the screens. The dynamics of such a screen is given by some unknown rules, which can be thought of as a way of processing the information that is stored on it. So the central argument of Verlinde is based on this principle, which to some people sounds very strange, but string people believe strongly believe in this principle. Well, there are a couple of names that must be mentioned. Bekenstein, which is a Mexican physicist, discussing the thermodynamics of black holes, and proposed that the entropy of a black hole is proportional to the area of the black hole. So the area of the black hole is the area of its event horizon divided by the Planck area. This hypothesis of Bekenstein was proved in 1974 by Hawking, who determined the temperature, which is called Hawking temperature of a black hole. And now we come to the argument of Verlinde. He will try to show that gravitation can arise from a thought experiment that he performs on black holes. So he starts his ideas with Bekenstein's original thought experiment, from which he obtained his entropy formula, the entropy formula for the black hole. He considered a particle of mass m attached to a fictitious string that is lowered toward the black hole. Just before the horizon, the particle is dropped in. The mass increase of the black hole is arbitrarily small. The Compton wavelengths of, if a particle has a mass m, then it has a Compton wavelength given by this equation. And when a particle is one Compton wavelength from the horizon, it is considered to be part of the black hole. This particle then increases the mass and the horizon area by a small amount, which Verlinde identifies, and also Bekenstein, with one bit of information. So 1 bit of information is a particle of mass m added to the black hole. And based on this idea, Bekenstein obtains his area law for the black hole entropy. And Verlinde will mimic this reasoning. His reasoning in principle is non-relativistic. he considers non-relativistic space, considers a small piece of a holographic screen and a particle of mass m that approaches from the side at which space-time has already emerged. On one side of the membrane, which he will link to the osmosis membrane, on one side of the membrane, the physics is described by macroscopic variables such as the position of the particles. The physics on the other side of the screen are formulated in terms of microscopic degrees of freedom, which are unknown. Those are the microscopic degrees of freedom describes the physics of the physics rules of the screen, and they are unknown. The holographic principle tells us that we can imagine that information about the particles in space can be mapped on the screen that separates the two regions. When the particle is dropped on the membrane, then the particle merges with the microscopic degrees of freedom of the membrane, but before it does so, it already influences the amount of information contained in the membrane. And Verlinde postulates that the change of entropy associated to the information on the particle dropped on the screen is 2 pi times the Boltzmann constant, and the displacement delta x is just the Compton wavelength. Combining things, then he states that when we drop the particle on the membrane, the entropy increases in this fashion. So we have a concrete number to the information gained by the screen when one particle drops on the screen. And now he says, okay, I will conjecture that now things works like in osmosis. Remember, this is the law of osmosis. So here, in this law, he puts his delta S of the information gained by the screen when a particle of mass m is dropped on the screen. And then he says this law is still operating. The process in his Soto experiment, he's describing a process that he says obeys the laws of osmosis. That is a second conjecture of Verlinde. Now we need still another effect, not from Holland, but from Vancouver, which is called the Unruh effect. The Unruh effect says that an accelerator observer will observe black body radiation, where an inertial observer would observe non-radiation. Then, to an accelerating reference frame, the Unruh effect associates a temperature to an acceleration in this fashion. Boltzmann constant, the temperature of the Unruh effect is h bar times the acceleration divided by a constant. So now we have also a temperature. Why do we need a temperature? Because in the osmosis frame, in the osmosis equation, we have the force, the displacement, a temperature, and an increase in entropy. And we have, in Verlinde's Soto experiment, we have already an increase in entropy. We have already a a displacement, which is the Compton wavelength, and now we have a temperature, so we can determine which is the force. So these are the questions. The displacement that we need in the osmotic force, which is in the middle. The displacement is the Compton wavelength. Then we have the increase in entropy of Verlinde. Then we have the en route temperature. And if you combine everything, you get, what do you get? You get this. It's not marvelous? If you believe all that, the two assumptions that Verlinde made, then you get immediately from the osmosis law, Newton's law of movement. Believe it or not, but it's quite simple. Remember, he has made some big assumptions. He believes in the holographic principle, for instance, which probably people who are not string theory people, we do not have any reason to believe in that. But let's accept it for the sake of Verlinde, who is a string people, and for him it's quite reasonable. So he got already Newton's law of movement, which is quite an achievement. Okay, this is what I showed. Let's see how he gets gravitation. To get gravitation, he will perform the same experiment, but the membrane now is a sphere. Before, to get the second law of Newton's, he got a plane membrane. Now he has a sphere. And so we have a closed surface. And the maximal storage space, or total number of bits of information that we can have on the sphere, is proportional to the area A of this enclosing boundary. Each fundamental bit occupies 1 unit cell. He says, okay, let's call n the number of bits. This number will be proportional to the area. And he writes this in this way. This G is the G of gravitation, but at the moment it's just a constant. So it could be a definition of the gravitational constant. It's the area of the surface, the number of bits, the velocity of light, and h bar. So the only unknown here is G. But we don't need to think at the moment that this has anything to do with gravitation. It's just a form of writing the total number of bits of information that are contained in a closing surface of area A. So here, the only assumption is that the number of bits is proportional to the area, but this is what Bekenstein said, so it's not some new assumption of Verlinde. Now, suppose there is a total energy E present in the system. And another assumption, he assumes that this energy is evenly divided over the bits n. So the entropy should be this division of the energy over the bits n is just the equipartition law. The equipartition law would be here the average energy per bit. Now we know that the energy can be written in terms of the mass and the velocity of light, of course. What is this capital M mass? This is the mass that would emerge in the part of the space enclosed by the screen. So inside the screen, let's say there is, since the screen has energy E, we can assume that there is a capital M mass. This is a mass associated to the energy that we assume is stored evenly on the screen according to the equipartition law. And now the rest is straightforward. I will collect all the equations together immediately, but we again start with osmosis. We have a value for the increment of entropy. The only new equation that we didn't have before is this one. And if you collect this together, you see gravitation. This M is the M that is dropped on the screen in the Verlinde-Sott experiment. This M is inside the screen and is proportional to the energy stored by the screen. And then if you believe the assumptions made thus far, then you have here the law of gravitation. Oh, it's the radius of the sphere. Yeah, but you are right. I should have. So I don't know if I have convinced you. You have to accept a lot of assumptions, but the assumptions are look innocent. And if you collect them, you have very simple equations. And out of those equations, you get gravitation. So, I mean, I would have liked to have done these equations myself, but unfortunately, this was done by Verlinde. So, what can we do now? No, this is classical. Oh, then he makes a lot of talk about okay, string particle talk, which I don't understand. But I could follow him up to this point. Ah, yeah. Then you should claim that to be cited by oh, this, but I don't think Verlinde cited that. Yes. Oh, okay, I would like to know that, yeah. Oh, very good. Okay, let me tell you what we did. We did the statistical mechanics. So, when you do statistical mechanics, you start with the simplest possible example, the ideal gas. And we look at the possible entropic force that this ideal gas would have. And we proceed, first of all, classically, and then we investigate the classical limit for bosons, fermions, and relativistic. And then it's very simple. You just have to compute the partition function. With the partition function, you get the mean energy, you get the free energy, and you get the entropy. And then we compute the gas entropy, and once we have the gas entropy, we follow Verlinde in thinking that the entropic force is the radial gradient times temperature, and that will give the entropic force. So for all we need is this equation. And the radial force, entropic force, is proportional to the temperature times the gradient of the entropy. We saw already that the entropic force has the potential, has the entropy as its potential.
And what is the proportionality constant?
Well, that is where we insert the Newton gravitational constant as a proportionality factor. Okay, this is the Q partition function for an ideal gas. It looks awful, but yeah, this is the classical partition function in momentum space for a Q gas. This is the Q exponential. So you have closed expressions for the partition function, the mean energy, and the entropy. Now we have to put a value for Q. We take 3 dimensions, nu equals 3, and Q equals 4/3. Then we should have a proportionality between some constant, the gradient of the entropy, and the temperature, and we get this equation for the entropic force. And you see that we get Newton laws. But this is a derivation that only assumes that you can write the proportionality constant in this way, lambda of 2 masses. But the derivation is straightforward. You don't insert nothing from outside. You take the classical gas, calculate the Q entropy, calculate the gradient of the Q entropy, and you get the Newton law. So this was considered to be, by Verlinde himself, to be a proof, a classical proof of priming. Okay, but I am finishing. Yes, you change. You get R squared only for Q equals 4/3. And dimension equals 3, yes. Yeah, good point, yes, good point. Otherwise, you get other laws, but of course, one wants to get Newton's laws. Well, some people in India calculated the relativistic partition function for a relativistic ideal gas in Sally's entropy. It's an awful expression, it's all this. But once you have it, we took it and we calculated the classical limit, and we get in the classical limit of the relativistic Sally's partition function, you get exactly the classical Sally's partition function, so there is no problem in showing that the non-relativistic limit of the relativistic partition function gives Newton law also. Then we did the same for bosons and fermions. This needs a special treatment, which is described in this book. A very nice book for statistical mechanics. So we took the equation from that book, adapted it to the Sally formalism with Q equals 4/3, and we got the entropy for bosons, the Q entropy for bosons and fermions. And we showed that the classical limit gives also the Newton entropy. But with a small detail which is of importance. Look, this is the entropic force for bosons. There is no divergence of the entropic force at the origin. It's 0. So the entropic force for bosons does not diverge at the origin. And at very large distances, it is Newton's law. And for fermions, we obtain the good limit, the classical limit for Newton. But space or distances cannot be smaller than this quantity. There is a lower bound to space. This lower bound is much smaller than Planck's length, but you cannot reach the origin because if you get very close to the origin, the entropic force becomes imaginary. So here there is a kind of quantization of space for fermions. But in the classical limit, you still get Newton's law. So to finish, to finish, what we have done is to make, to devise a simple classical mechanics proof of Verlinde's conjecture without appealing to any holographic principle or things like that. And at this level, at the statistical mechanics level, we show that the conjecture of Verlinde works. That at the level of an ideal gas, its entropic force, then the entropic force of an ideal gas gives Newton's law classically, and at the classical limit of special relativity, fermion statistics, and boson statistics. Questions become interesting when we are not in the classical limit, because then new phenomena appear that could be of some help in understanding what features of gravity have to be modified to account for dark matter. Because at short distances, the quantum entropic force is not equal to Newton's law. It's different. Has a different radial dependence. Okay, so that is all. Thank you very much.
Thank you, Professor. Questions?
So I have, first of all, I have one question about motivation. One of the first pages that you put.
Yes.
As far as I understand, the original motivation by Verlinde was not to define some modified gravity, was just to show that the gravity should not be quantized since it is emergent.
Yes.
But I have one question about your first page, because at the beginning of the year, there was some data from astronomers that proving there are some galaxies where they detected no dark matter. And then the point was, since they detected no dark matter, this means that the dark matter is real, because it rules out modified gravity, because otherwise modified gravity should be seen by all galaxies. Do you have any comment about that?
No, I am not an expert on anything related to astronomy. I just read that Scientific American and was impressed by it. See, I know what you mean.
Mm-hmm. Do you know which month was this Scientific American? Because August. Mm-hmm.
Yeah.
Mm-hmm.
I just read this. That this article, which is from August, that they say that there is astrophysical evidence in favor of mobility gravity models, but that's the only thing I really know about that.
Mm-hmm. And then I have another question. So you have this formula you modified for the relativistic gas.
Yes.
And then you computed the entropic force. May I ask you, is it possible also to derive deviation of Newton's law, for instance, in the, let's say, like the perihelium of mercurium, which are origin from general relativity? So if you impose a special relativity, do you have some? Can you find a deviation from standard Newton law at?
No, I don't think so, because you see that is the partition function of an ideal relativistic gas,
Mm-hmm.
and nothing more than that. And it's not a two-body problem that we could. It's not a dynamic two-body problem. It's a statistical problem only. Yes, but it's already awful to derive for the. I mean, we looked very hard to see if someone has some relativistic partition.
No, I know.
Function,
Here is
and we only found relativistic
the ideal
partition
gas,
functions
but
for the
if you
ideal
have
gas.
some unknown potential, could be.
No, with potential, it can be done for sure, but we were not able to find one already done. And by the principle of maximum commodity or easiness, if we don't find the partition function, we go to another subject.
Okay. Just to understand, so you say you have this ideal gas, but this is already some effective description, no? Because ideal would be Q equals 1, so the 4/3 is already some, due to some long-range interaction, or
that's an interpretation. Why ideal should be Q equal 1? You could have an ideal gas with Q equal any number.
So, okay, my understanding was always that this is some effective description if you have like long-range interactions or something like this.
Yes,
and then
yes.
it is.
It's in a sense, it's an effective.
And the 4/3 would appear if you have long-range interactions, or because I just there's some.
Well, we have the expert here.
Yes. So under which conditions would it?
Yeah, long-range interaction is one of the arguments in favor of Sally's statistics.
But it would increase the Q or decrease the Q. So that is what. How is like under which conditions would you get? Is it? I don't know if it's possible to answer this.
What has been calculated is the value of Q corresponding to distribution of momenta and distribution of energies. Both Q are above 1. Above 1. Nobody has calculated in the presence of long-range interactions what is the value of Q of the Q entropy that becomes extensive. This could be Q below 1, I don't know. But what is clear is the distribution of velocities or momenta and the distribution of energies. These are both of them above 1. In fact, Fernando Nobri is co-author of that recent paper. And the value of Q for the distribution of energies for the XY model. No, but he's referring in the presence of interactions. It's
yes.
not an ideal gas. It has kinetic energy plus the interaction. The value when the interaction is very long range happens to be Q equal 4/3, the value that he mentioned. This
Also
is
just-
in our paper.
That's a nice coincidence.
I don't know if it has any
Yes.
connection with more,
But this Q said, yeah, that's very interesting.
Okay, you want to talk? Okay, then we will have a coffee break now, and we come back in 20 minutes.